Mr. Tarou, in this trigonometry lesson, we're going to be doing 4 word problems based on the definition of bearing, the direction in which you are traveling. And our 4 examples, well, the first one is going to involve a little right triangle trigonometry, some SOHCAHTOA. Our second example is really just going to ultimately be solved once we get the diagram set up correctly, Pythagorean theorem. And then the last 2 examples, we're going to take the second example and tweak it a little bit so that we can't solve it quite so easily, and do some examples involving law of sine and law of cosine. Okay, so depending on where you are in your trigonometry studies, you might have already learned all those concepts. Right, SOHCAHTOA, Pythagorean theorem, law of sine and cosine. I already know all that stuff. Why am I watching this video? Because bearings is different than your standard position angles. How so? Well, there's 2 ways of stating bearing, and plus, setting up diagrams from word problems are not very easy sometimes. So if stated as a single angle, this represents a clockwise rotation from due north. So if I say we're going at a bearing of 126 degrees, well, then I would reference a sort of a north-south line. Let's keep the color coding all consistent. We have a due north line, right, rotating from north. We're going to rotate in a clockwise direction, and I'm not using a protractor here, so just doing my best guesstimate. That's a little bit 36 degrees more than 90. So this white ray would indicate movement at a bearing of 126 degrees. Standard position angles start on the positive side of the x-axis and rotate counterclockwise for a positive angle measure, right? Well, now a positive angle measure, at least in terms of bearing, starts at due north, a completely different direction, and rotates clockwise instead of counterclockwise. So setting up the diagrams is a little bit difficult if you just have those standard position angles stuck in your head. Another way of indicating bearing is you might just hear this language a lot in the newscast when they're talking about the direction of the wind, or looking at a compass, of course. Bearing is all about really looking at a compass to indicate direction. Start with a north-south line and use an acute angle to indicate a west or east direction. So some examples of that, we have north, 40 degrees east. So we're going to start by referencing the due north line. We're going to rotate 40 degrees in an eastern direction. We're not talking about positive or negative angle measures here, so we're just going to say, well, here's north, south, east, and west. East is to the right, if you will, and so we're going to, from north, rotate, okay, again, no protractor, but approximately 40 degrees, and it's going to look like a direction such as that, with 40 degrees in between the actual arrow indicating bearing and north. South, 80 degrees west. Okay, so from the north-south line, we're referencing south, so we're referencing this sort of downward position, if you will. We're going to rotate, again, that acute angle in a western direction, so we're going to rotate to the left as opposed to rotate to the right towards east like we did here. And, okay, not a very good arc there, but 80 degrees, and a little bit less than 90, of course, and maybe this white ray would indicate a direction of movement in the bearing of south, 80 degrees west. And that is how you look at a bearing notation, a bearing angle, and you set up an indication of direction in which you're going to move. Now, really the most important, or maybe difficult aspect of doing these word problems dealing with bearing is getting the diagram set up. Your textbook will probably give you diagrams to match some of your earlier problems, but ultimately we need you to be able to read a word problem and get that diagram set up, and let's start that right now. Bam! Much better. Alrighty then. Radar stations A and B are on an east-west line, 5.3 miles apart. Okay, so let's see here. Let's go east-west line. I'm not sure if A is going to be here and B is going to be here, or B is going to be here and A is going to be there, but they're east and west of each other. The helicopter is identified at a bearing of 23 degrees from station A. Okay, so this is a bearing, so I'm referencing the north-south line, and let's put in a north line here and a north line here. As you set up these diagrams, by the way, the north-south line is going to, basically be intersected by these transversals, and so you'll be using some alternate interior angles or same-side interior angles, some definitions that you started learning in geometry, and you use those properties to find some of these missing angles to set up the diagram. And so I'm either going to be looking at a direction of 23 degrees from, maybe A is over here, or maybe A is over here. Okay, so somewhere in this sort of like 23-degree angle direction bearing, there is a helicopter. Now when I go to the rest of the problem, it says, well, in a bearing of 293 degrees from station B. So if I put A over here and I rotate a bearing of, and go on a bearing of 23 degrees, or rotate 23 degrees from north, then from B, okay, well, if I put B over here, look, my rotation is going to be less than 90. So this can't be the proper orientation where A is on the right-hand side of my diagram. So let's keep A on the left. And this is no good. And neither is this dotted line now. And I've got an indication or a marking of 23 degrees bearing for where this helicopter is from station A. Now, if I rotate 293 degrees from station B, so due north, okay, so we're looking at bearing, so from due north, and we're going to rotate 90 degrees, and we're going to rotate 180 degrees, and we're going to rotate 270 degrees, but our bearing is not 270, our bearing's more than that. Our bearing is another 23 degrees past 270, so we're going to rotate and have a bearing that looks something like this approximately, and that's 293 degrees, at least as a bearing. And now it makes sense that from station B we're going to go out and basically have an indication of where the helicopter is from bearing B, or from station B, excuse me, and from station A. And we have a triangle set up. I almost said right triangle, but we don't really know that yet. Okay, well, let's see here. The stations are 5.3 miles apart. Okay, now we have that number in there. And that's it. So we need to work with, well, some kind of information. We're looking for how far the helicopter is away, and let's just call that point C. We're finding out how far that helicopter is, or this intersection point C is, from station B. So we're looking for this value right here. Okay, now here's where we need to start looking at more information. And remember that, yes, we have basically a yellow-white triangle in here, but we have these due north lines, and we're going to use that information, like north and south line, and compared to the east-west line, well, that's what? Perpendicular, 90 degrees. So if that's 23 degrees, and this entire angle between north-south and east-west is a perpendicular angle, a 90-degree angle, well, 90 minus 20 is 70, minus 3 is 67 degrees. Great. Now, let's see. Well, 293, and did you remember how I counted that out? Rotating from north to east is 90 degrees, and then from east to south is 90 degrees, and then another 90 degrees to go to west. And so 293 minus 270 means we have a remaining angle of 23 degrees, and that's that little piece right here that's actually inside this triangle that we're creating. And so we have 23 degrees. Oh, okay, so, well, I can see 23 here and 23 here, and, okay, I could just look at that and go 90 degrees. Or 60 and 20 is 80, and now we're at 87, and another 3 is 90. So the two acute angles of this triangle is 90 degrees, 180 degrees in a triangle. So the remaining angles, or degrees, left is 90 degrees, and thus we have a right triangle. Now, in this right triangle, we only know one side, and we're trying to find a missing side, which means, well, to find missing sides of a right triangle, you're going to be doing either Pythagorean theorem or SOHCAHTOA. SOHCAHTOA. Sine is equal to opposite over hypotenuse, ka. cosine is adjacent over hypotenuse, and TOA, tangent, is equal to opposite over adjacent. Let's see here. I'm sure I have a lesson on right triangle trigonometry. If you need that, I will put a link in the description of this video, of this lesson. And when you try to decide if you're going to use sine, cosine, or tangent, and you're doing right triangle trig, you need to decide what angle am I going to work with. Let's see. Let's highlight this in red. I'm going to use angle 23. It doesn't make any difference. Now, if I'm going to use angle 23, then the side opposite the right angle, of course, is always going to be the hypotenuse, and the leg that is helping to create that acute angle, or the one next to it, is the adjacent angle. And then over here on the opposite side, we have a length which maybe is interesting in another question, but we don't care about it here. What do you have and what do you want? What do you have? What do you want? What do you have? I have a hypotenuse of 5.3 miles, and I want the adjacent side. Adjacent hypotenuse, that means that we're going to use the cosine function to finish this problem. If I decided to work with 67, then that wouldn't be the adjacent side to 67, that would be the opposite side, and we'd be using sine. So there's multiple ways of working out this problem. The cosine of 23 degrees is equal to the adjacent side, which I'm looking for, which is x, over the hypotenuse. The side opposite the right angle, or 90 degrees, is 5.3. Once you start dealing with sine, cosine, or tangent, or secant, cosecant, and cotangent for all that, for what that's worth, but most calculators only have a sine, cosine, tangent button. If you're touching one of those buttons, you need to make sure your calculator's in the right mode. Sometimes we want radians, actually very often in trig, and pretty much all the time in calculus. But, you know, there are times when working with degrees. So if you touch sine, cosine, or tangent, make sure you check the mode of your calculator. We need to be in degree mode. And, of course, we want to just undo this division of 5.3, so we're going to multiply both sides by 5.3. And when we do that, we're going to get that, well, I guess I can just write this out. X is 5.3 times the cosine of 23 degrees, and x is approximately equal to, right off the top of my head, voila, hopefully I got this typed into the calculator correctly. I did check my work, and it's approximately 4.8 miles. And that is the end of my first example. The next one is also going to set up to be a right triangle, but it'll have a little bit different reading, so let's look at it right now. A ship travels 65 kilometers on a bearing of south 19 degrees 10 minutes east, and then travels 192 kilometers on a bearing of 70 north 70 degrees and 50 minutes east. How far is the ship from where it started? Okay, so let's just give this a nice open space to start setting up our diagram, and we're starting off southeast, so kind of down and to the right. So probably this is a decent place to start. Put our orange north-south line. And we're referencing south first. So from this point, we're going to rotate basically 19 degrees or 20 degrees or whatever. But again, I'm not using a protractor, so let's just call that 19 degrees in 10 minutes. Okay, I want to make sure I have enough room to work here. Let's just make that a little bit longer. Now, then it turns, and it travels 192 kilometers. Oh, the distance would be nice. 65 kilometers. Put that in, oh, I don't know, green. 65 kilometers. And then it turns and goes 192 kilometers on a bearing of north 70 degrees 50 minutes east again. So we're still going towards the right, but now we're kind of going a more northern direction as opposed to south. And that means we're going to use another north-south compass line, if you will. And I don't want to get this too messed up, so let me just put south down here. North and 70 degrees, almost 71 degrees east. So let's see, that's 90, somewhere in the middle is 45, so maybe something to that effect. And we're going to go out in this direction. I'm making this much longer, of course, because not that this is going to be a perfect scale, or for that matter, perfectly straight. You don't need an arrow because we're not going to go an infinite distance. And we're going to go 192, let's do that in green, 192 kilometers. And that angle right there, 70 degrees, and 50 minutes. And how far is the ship from where it started? So we went along this path, and the side that we are looking for, let's label it or draw it blue. How long is that blue line? How long is, let's just call it x. Am I going to need law of cosine, law of sine? Can I just use some basic right triangle trigonometry or Pythagorean theorem? Well, these north-south lines are parallel lines, and we've got some angles. We've got an angle here, this 19 degrees and 10 minutes is this little angle right here. Parallel lines cut by a transversal. The same side interior angles are going to be supplementary. So this angle here where my finger is and this angle out here would be supplementary, so they'd add up to 180 degrees. And alternate interior angles are going to be congruent, of course. When parallel lines are cut by transversal, alternate interior angles are congruent. And I need angles inside that triangle so I know how to approach the problem. So I have the 19 degrees 10 minutes for this angle right here, but it's also this angle right there. All right, so how big is this entire angle inside the triangle? Well, I guess we could do that in yellow. Let's do 19 degrees and 10 minutes. Add that with 70 degrees and 50 minutes. We're going to handle the minutes and the degrees as sort of like two separate columns. 10 and 50 is going to be 60 minutes, and 70 degrees and 19 degrees, well, 70 and 19 is 89 degrees. Well, we know that a minute is a part of a degree, and 60 minutes makes up a whole degree. So I can sort of take away all these 60 minutes and put it into the degree column and get that that angle is 90 degrees. So we have a right triangle. And so let's put a little perpendicular mark in there. And I'm looking for the side, that blue disc, that blue line. The ship started here, it came down southeast and then headed northeast, much longer distance. And how far is the ship? Oh, let's see here. There we go. Oh, beautiful ship. That ship is, I guess it should be in the same direction as the white line, but how far is it from where we started? Well, I'm just missing one side of a right triangle. Nothing fancy there. That is Pythagorean theorem. What's up? So we're going to do one leg squared, which is 65 squared, plus another leg squared, 192 squared, and that is going to be a squared plus b squared is equal to c squared. And, you know, right off the top of my head, because I can do 65 times 65, you know, piece of cake. Oh, actually, I guess, well, maybe when I was writing these notes, I thought, you know, trig students don't need to have me show every single step. So 65 squared plus 192 squared comes out to be 41,089. That's equal to c squared, and of course we need to square root both sides of this equation. And the distance that ship has traveled, yes, a ship, not an airplane, is approximately equal to, man, like 202.7 miles. And I'm putting an approximation symbol, of course, because, whoops, why did I put another decimal? Oh, I didn't, because it's supposed to be the dot on the I. But 202.7, that's a rounded off value, so I'm just using approximation because it's not exact. And that is the end of our second example. Now we're going to get into law of sine and cosine. You know, what if I just manipulated this problem a little bit so that these two angles didn't add up to 90? So we've changed our new bearing to north 68 degrees and 15 minutes, and you see that I'm still, of course, using those alternate interior angles, taking the 19 degree 10 minutes, adding it to our new 68 degree and 15 minutes, and we get a new angle in here, a new combined angle, which is approximately 87.417 degrees. I got rid of the minutes and got to a decimal approximation because, well, of the work coming up. Well, now it's not a right triangle, and we can't do, Pythagorean theorem to find the missing side of this triangle. So the information given, and I know it's getting a little bit sloppy here, but we have a length of 65, we have an angle, an inside angle of 87.417, and another side of 192. So with this 87.417 degrees is in between, or included in these two sides of 65 and 192. And as we walk around this triangle and sort out the information given, it's in a side angle side pattern. Well, side angle side, hopefully you reviewed this when studying your law of sine and law of cosine, is a congruency theorem from geometry. And so there is only one possible triangle we can make with this information. And when you know two sides of a triangle and the included angle, you're going to work through that using the law of cosine. Now, there's no way that you can set up law of sine with information given in that pattern. I'll put links to those lessons too, law of sine and law of cosine, if you haven't studied that yet or you need a refresher. So that means that I need some angle labels up here so that I can set up this law of cosine and finish the problem up. So we're going to have point A, point B, or in vertex, I should say, C. And of course the corresponding sides are opposite those angles. So if this is angle A, this is side A, angle B, side B, angle C, side C. And the law of cosine, there's three versions, but it kind of all says the same thing, that the length of a particular side, and we're looking for side B, squared, is equal to the other two sides of your triangle squared, so A squared plus, in this case, C squared, minus 2 times those same other sides. So we're looking for side B. So B squared is A squared plus B squared minus 2 times AC times the cosine of this angle opposite the side that you're looking for. So it's going to be 2 minus 2AC cosine of B. And now we have B squared is equal to A squared, 192 squared, plus C squared, which is 65, minus 2 times 192, I'm running out of room, times 65 times the cosine of 87.417. This is why sometimes I pause the video, because I run out of room. So let's pause the video, rewrite that line so it's a little bit easier to read, and look at the steps that that's required to find the approximated value length of side X, or now with my new labels, really that's going to be side B. All right, so you saw I had equal signs, and then I came back and did little approximation symbols. I wouldn't mark off for my students doing that, but I've had some people on YouTube, some of the smarter people, more strict people say, hey, this was an approximated value, so this isn't exactly equal. But at any rate, we have that B squared is equal to 65 squared plus 192 squared minus 2 times 65 times 192 times a cosine of 87.417 degrees. Now, I teach this material to honor students, and it's so easy, though, to get caught up in not following the basic order of operations. And I see students all the time, clean all this up, and whether they put it on their calculator at one time or even they write this line, 65 squared plus 192 squared is, again, that 41,089, and 2 times 65 times 192 is 24,960. And then they just, subtract these two numbers and have some value times the cosine of whatever your angle is, in this case, approximately 87 degrees. Well, of course, that's not correct. We have to multiply before we add or subtract. So the 24,960 times the cosine of 87.417, making sure your calculator's in degree mode, that comes out to about negative 1124. And, you know, combining like terms and square rooting, we get a distance that ship is from its original starting point of approximately 199.91 kilometers. Now, what if, now that we know how far the ship is from its original starting point, what if we wanted to sail directly from directly to C from A? What would the bearing have to be? So if the ship, again, wanted to sail directly to C from A, at what bearing would it travel? Just put it in words, right? Okay, so I left all this up here, and what bearing? Okay, well, I'm going to be referencing, you know, north or south. I try to draw this somewhat to scale, so I think that that's going to be an acute angle. I don't have to do north, you know, something east. I can just make an angle measure off of due north. I need to find out what this bearing is right there. Okay, well, remembering again that these north-south lines, you know, yes, it's all about the triangle, but we need to use those north-south lines like I did here as an example with those alternate interior angles. They are part of the diagram. And, well, I've got an angle here which is 19 degrees and 10 minutes. And I got a lot of information about this triangle, so I'm sure it's not going to be very difficult to find the measure of this angle. And then I would have 1, 2, 3 angles, you know, basically all adjacent to each other, forming a straight line. Now that's, you know, not a linear pair. Linear angles is a pair of angles that are supplementary or that form a straight line. But yes, these 3 angles, while you can't call them some kind of special name unless there is something out there I'm not sure about, but they do add up to 180 degrees. So if I know, you know, I know this angle, if we find this one, this particular angle inside the triangle, we can subtract those 2 angles from 180 degrees and find out what that bearing is. Now, with all the information given, we know all 3 sides of this triangle. We can use the law of cosine to find that missing angle. And at times, it would be a very good idea to use the law of cosine to find a missing angle inside of a triangle. Indeed, it might be a safe bet to sort of simply always use law of cosine to find missing angles inside of a triangle, because when you do inverse cosine, remembering your restrictions on your inverse trig functions, inverse cosine acting as a function, you know, basically the kind of numbers you get out of your calculator, inverse cosine is going to give you answers, your calculator, restrictions of the inverse trig function, between 0 and 180 degrees, or between 0 and pi when you're working with radians. Whereas inverse sine can only give you answers between negative 90 degrees, or negative pi over 2, and positive pi over 2, or positive 90, and we're working with degrees, so inverse sine can only give you answers between negative 90 and positive 90. So when you go to try and find an angle measure that is opposite the biggest side of your triangle, there is a possibility that that angle is going to be obtuse. And if you try and use law of sine to find an angle opposite the biggest side, if that angle is obtuse, you are not going to get the right answer from your calculator. And there's a pretty decent chance that you're not going to catch that error unless the problem is very well drawn and very close to scale. So when finding an angle opposite the largest side of in a triangle, you really want to use the law of cosine so that you get that obtuse angle when needed. But that's all just verbal review. 192 is not the biggest side of this triangle. 199 is, so there's no, well, 0.9. So there's no way that angle CAB can be obtuse. So since you saw one demonstration of law of cosine, let's do a review of law of sine. So law of sine, your book might write it as the sine of A over A is equal to the sine of B over B, and that's equal to the sine of C over C. And then some books will have it so that the sides are on top and not the sine function, and have A over sine of A, B over sine of B, and C over sine of C. You know, either way works. Now you can't work with all 3 parts at the same time, So let's say we're going to work with, we have angle B and side B, and we have side A, and we're going to look for angle A, and let's work with this portion of the law of sine. So the sine of, okay, well, you know, I guess it really should say CAB. So, you know, there's three angles there. But at any rate, the sine, I'm just going to call it sine of A. The sine of A over the side opposite that, which is 192, is equal to the sine of B, and that's going to be the sine of 87.417 degrees over side B opposite angle B, which is 199.91. We're going to, you know, looking for angle A, so we need to get the 192 away from this trig function. So now we have the sine of A is equal to 192 times the sine of 87.417 degrees all over 199.91. And we're going to get that into our calculator, and that, right off the top of my head, is approximately, let me make sure I haven't written anything wrong, okay? So that means that the sine of A, get into my low down stance here, is approximately equal to, you could argue, oh, this is approximately equal to 0.95946. That means that A is going to be approximately equal to the inverse sine of 0.95946. And that is, you know, approximately equal to 73.63 degrees. And so we have 19 degrees in 10 minutes. We're going to take that 10 and divide by 60 to convert it into a decimal approximation. But anyway, basically 19 degrees. We have 73.63 degrees. And now that remaining piece is our bearing coming off of north. So X, do we need another color? I think I pretty much used them all. Let's go to, well, I'm out of colors, but let's call that X now. And so X, whoops, is equal to 180 minus 19. Now, 10 minutes divided by 60 minutes to convert that into a decimal approximation is approximately equal to 19.16, where'd my 1 go? 0.167 minus 73.63. Yes, right there. And so X is approximately equal to 87.203. And so my bearing, you can say, is 87.203 degrees. And if you want to write it in sort of that northeast relationship, it's going to be north 87.203 degrees. And we're going towards the right. So again, that is going to be east. And that is the end, chalk down, of my last example. I'm Mr. True. Bam! Go do your homework.